My topic for the next half hour is the presence of Indian mathematics in the mathematical mainstream. And this talk is drawn from a series of talks that I have given in the past few years, mostly to audiences of school and college age students who are of Indian origin but live in the United States. I work as a volunteer in the temple in my hometown, and which has a very robust educational program where all kinds of programs are offered to children and adults. We teach most of the major Indian languages, including Sanskrit, some of the various schools of dance, music, religious classes, philosophy, mythology, and so on. But science and mathematics is something that is lacking. There's a lot of interest among this age group, students who know in some vague way that there is a lot of Indian heritage in this area, but they don't have any clear information on this. So whenever possible, we include small modules as part of, say, the annual day, Sanskrit day, summer camps, weekend camps, and so on. So I've put together a few of the ideas from there, which are definitely going to be very elementary to the learned scholars in this gathering, but hopefully will be of some interest to the general public, definitely the college students, to give you a close-up view of how these ideas are expressed in Sanskrit. So as I said, besides the need to create this general awareness among students, what we also try to do is develop the understanding that multiple knowledge systems can exist, which prove the same results. And because we are used to the intellectual conventions of one knowledge tradition, it doesn't mean that other knowledge traditions should be neglected or sidelined. And also to highlight the interconnections that exist between what are normally thought of as very disparate fields like math, art, and poetry. Typically, we see a lot of school students say, I'm a math person, I don't like literature, or I'm a humanities person, I cannot understand mathematics. So this is to show that some of the finest minds in our traditions, for instance, the mathematicians were not just mathematicians, but also very learned in the Vedas, New Grammar, Tarka, astronomy, all these different things, and they straddled all these different fields with relative ease. And finally, to celebrate our own achievements, because if we don't, who will? So these are some of the topics that I've picked. I don't know if I will have enough time to go through all of them, but I will definitely give it my best shot. The Pythagorean Theorem is something that we have heard a lot about. We know that this is named after a Greek scholar called Pythagoras, who lived around 500 CE. But however, the first documented evidence in terms of actually mentioning this theorem by this name only happens around 400 CE, which is more than almost 1,000 years after the time of Pythagoras. However, in the Indian tradition, it appears in the Baudhayana Sutras of around 800 to 1000 BCE. And it is also listed in the form of the mention of certain Pythagorean triples in some Babylonian tablets that can be dated back to around 2000 to 1500 BCE. There is, of course, proof of the Pythagorean system that exists, of the Pythagorean theorem that exists in other cultures. This is one of the most common proofs, which is found in several traditions, not ascribable to any particular person. Mostly geometric in approach and takes a cut and paste approach to proving the theorem to show that the area of these two squares on the sides of the right triangle can be shown to be equal to the area of this slanted square, the area of the hypotenuse, because what's left over these two triangles are equivalent to these four congruent triangles. However, the first rational proof of the Pythagorean theorem is as seen in Euclid's Elements. It's commonly called the Windmill theorem because of the shape of the construction. And it starts with the basic definition. It actually appears in his book 1 and it is sort of the jewel in the crown of book one, which starts with basic definitions like the definition of a point and so on, and then goes as a set of sequentially reasoned logical steps, and finally culminates with the proof of the Pythagorean theorem. It's a very elegant, well-reasoned proof. However, it's kind of long and tedious because it involves proving that these two triangles are congruent, then showing that the areas of the square and this rectangle are equal, then doing the same on the other side, adding them up, and so on. But because it follows a very rational sequence, and starting from first particulars finally arrives at a generalized conclusion which is universally applicable, it's quite often held up as being symbolic of man's ability for rational, intellectual, sophisticated thinking. There are other proofs also that exist in other cultures. In the Chinese tradition, there is this 10-gram method by the mathematician Liu Hui, which basically cut up these squares on the sides of the arms of the right triangle, and then reassembles these cut-up pieces to perfectly fit the square on the hypotenuse. This is like the 10-gram game that you might be familiar with. Other proofs in the Chinese system, the Zhubi book on math and astronomy takes a square like this with some specific values here, like in this case it's 3 by 4, and then goes to show that this big square, which has a side of 7, has an area of 49, which can be shown to be the area of this small square, which is 25, works out to the square of the hypotenuse. It's more of a taking a particular case. And then, of course, there are plenty of proofs for the Pythagorean theorem, something that people have loved to prove throughout the years. Da Vinci had his own proof, and even James Garfield, one of the presidents of the United States, came up with his own proof of the Pythagorean theorem. Now, looking at how this is presented in Indian mathematics, in the Baudhayana Shulba Sutras, this is the most ancient occurrence of this theorem, and it appears in sutra style, which is the earliest style of literature that we see, attributable to Baudhayana. And in addition to the theorem, also lists several instances of Pythagorean triples like 3, 4, 5, 5, 12, 13, and so on. And it also appears in later Shulba Sutras as well. So this is the Baudhayana theorem as it is famously stated in the Baudhayana Shulba Sutra. Dirgha chaturashrasya akshnya rajjuhu parshvamani tiryangmani cha yat pritak bhute kurutas tadubhayam karoti. So if you want to parse this phrase by phrase, Dirgha chaturashrasya, of a rectangle, parshvamani tiryangmani cha, the horizontal and the vertical side, yat prithak bhute kurutaha, what they do individually, the akshnya rajjuhu, which is a term that is used to refer to the hypotenuse, it does both of that, tadubhayam karoti. So on the face of it, this looks like it's somewhat vague and imprecise. It's no way to state a mathematical result. What do you mean that this does what the other two do? But again, to reinforce that this is written in the sutra style, which is very concise, only provides the absolute minimum of information as is necessary, and also it's not a theorem that's just out there. It follows a series of other sutras stated before that, one of which is this: Chaturashrasya akshnya rajjuhu dvistavatim bhumim karoti. Now this is referring to the case of a square, chaturashraha, and it says that its akshnya rajjuhu, its diagonal, does twice the area of the original square. And this is very obvious when you look at this diagram here. This solid line square has been cut by this dotted line, which is its diagonal, dividing it into two equal triangles. And if you build out a square on this hypotenuse, this is the dotted line square, and then draw its diagonals, the hypotenuse square is now divided into 4 identical triangles, which are in turn identical to the 2 triangles of the original square. So you can see that the square on the hypotenuse is equal to twice the area of the original square. Now, some people have said that, well, this is just a specific instance which only applies to a square, and nothing is said about a rectangle, which is what the Pythagorean theorem is about. But again, since only the minimum amount of information is typically conveyed in sutras, and the reader is generally assumed to know enough about what he is learning, what he is reading, so that he can make the necessary connections. If you think, for example, about the Ashtadhyayi, which is the epitome of sutra literature, it's completely cryptic, and nobody can really read it and understand it without the aid of a commentary or a qualified teacher. So in the same way, the statement that has just been made with respect to a square can probably be easily extended, a similar kind of reasoning, to a triangle here with sides A and B. If you draw your hypotenuse C, and then you try to extend a square so that you have a square to work with, you can build this little dotted line square on the side of side A, build out a bigger square here of side B, and then fill up this gap with a rectangle that's identical to the original one, so that you have a big overall square of A plus B. And then the side of this A plus B square, its area would be A squared, the area of this little square, plus B squared, the area of this big square, plus 2 times the area of these 2 rectangles. That's your first formula. And then if you build out a square on the hypotenuse, then the area of this big square A plus B is also equal to the area of this dotted line square C square, plus 4 congruent triangles on the side, which are each of area half AB. So looking at these 2 triangles, equations, you can see that C square here is equal to A square plus B square. So the same reasoning can be extended to say that the writer of these Shilpa Sutras probably was quite aware of the proof, even though it wasn't explicitly stated. Also, many of the other statements that they make regarding construction of a rectangle from a square from a rectangle, circling a square, squaring a circle, and so on, gives you a pretty reasonable conviction that they must have known the proof of this theorem. At the later stage, when literature became more versified and mathematical results were expressed in verse, we have the Manava Shulba Sutra, which puts the same Pythagorean theorem in verse form, saying ayamam ayama gunam. Here ayama is the horizontal side, guna being multiplied. So the ayama is multiplied by itself. Vistaram vistarenatu, the breadth, vistaram, multiplied by itself. Samasya, added together. Vargamulam yat, that which forms its square root, tat karnam tad vido viduhu, that is known to be the karna, which is the later term used for the hypotenuse. So this is an instance of how, again, mathematics is expressed in poetry. And in that same tradition, I tried to do this in English, and that's what I came up with. Here is a quick mathematical dare. Try it on an elongated square, which is what a chaturashrasya is. The length times itself, added to the breadth, so multiplied. Take its root, wise child, and the hypotenuse is derived. And the wise child there is just a nod to Lilavati of Bhaskara, where he addresses his reader as Bale, Vatsa, Mitra, Bala, Kuranga, Lola, Nayana, and so on. So that's one topic. Moving on to the next, the quadratic equation, which is something that most students have seen, just about everybody has seen in their school years. This is the expression that we're familiar with. I apologize for that. It's A not equal to 0. I couldn't transfer that gobbled it up. So here the earliest, this has been something that's been aware to, there is an awareness of this in many different civilizations. The Greeks knew of it certainly, but their proofs were more geometric, which involved the construction of squares and circles and so on. But we do see an awareness of this result in the Bakshali manuscripts as well. And excuse me for those dates. I just went with the most recent redating, and I put that. I didn't take the mean or anything. We see an awareness of this solution in the works of Aryabhatta, Brahmagupta, and Mahavira, who composed problems which involve this solution. But the first complete proof we see of this solution, meaning how to derive it, is by Sridhara of Bengal, who lived around 900 CE. He wrote 2 books, one on algebra, which is now lost, but it is quoted by Bhaskara and other commentators. And his book on arithmetic, which is Trishatika, still survives. So before we actually look at Sridhara's equation, I want to give you a little sense of What is the terminology used? We're familiar with ax squared plus bx plus c equals 0. How do you say that in Sanskrit? Where's the squaring and where's the equal and so on? So here's some of the terminology. The term, the word equation has been expressed as samakarana or samikarana, which is the equalizing of the two sides, the itarapaksha and the aparapaksha. And the familiar method that we use of solving quadratic equations by completing the square, that process is referred to as Madhyamaharana by Aryabhatta. And coming to the specific parts of it, the coefficient, interestingly, has no separate term used to refer to it. It's usually referred to by the power of the unknown with which it is associated. So a, for instance, would just be referred to as the x squared. But it's implied that it's the coefficient that is being referred to. And sometimes specific words are used, but more often than not, it's just the power of the unknown. The unknown itself is called avyakta commonly. In the earliest BCE Sutra literature, we see it referred to as yavat tavat. In the Bhakshali manuscript, you see it as yadricha, vancha, kamika. Aryabhatta refers to it as gulika, which literally means a pellet. Brahmagupta calls it varna, and the word varna is interesting because some people think that because varna in Sanskrit means color, that maybe at some ancient point equations involving unknowns had colors in them, different dots of color to represent the different unknown quantities. But because varna also means letter in Sanskrit, that practice may have later transitioned to the use of letters that stand for colors, such as ka, which stands for kalaka, meaning black, ni for nilaka, meaning blue, lohita, shvetaka, and so on. As far as the power itself is concerned, we see the words varga for square and ghana for cube in the most ancient literature starting from the BCE Sutra works. Later on, they adopted a more of a multiplicative kind of system where for higher powers, like for instance, the fourth power was referred to as varga varga, 2 times 2. The sixth power was referred to as ghana varga, ghana being 3 and cube and varga being square, so it became 2 times 3. Ghana varga varga, 3 times 2 times 2, the 12th power, and so on. Later on, that was modified into more of an additive system, varga ghana ghata, which ghata meaning multiplied. So it's more related to the exponential system that we're familiar with. So that was 2 plus 3, meaning the 5th power, varga varga ghana ghata, referring to the 7th power, and so on. But it was Brahmagupta who introduced a more scientific usage involving numerals. For instance, panchagata, which literally means raised to the 5th power, shadgata, raised to the 6th power, and so on. And the constant itself, the c in your ax squared plus bx plus c, which is literally the only part that you can actually see because the rest of it involves unknowns. So this part is called the rupa. So here's a couple of examples of quadratic equations so you can get a sense of how they look. So this goes yavat varga 0. And that refers to yavat being, as I mentioned earlier, the unknown quantity, the x. Okay, and varga means that it is squared. 0 is its coefficient, so that is 0x squared. And then you have yavat and 10, so that means 10x. And then you have rupa 8, and that refers to a constant, because rupa means constant of 8. And the 8 with the dot above it, they use that system to show that it's a subtraction. Okay, I put it on the side, I couldn't get it quite on top, but it's usually a dot that goes over the number. So this equation becomes basically x squared times 0 plus x times 0 minus 8. And the one below it, yavat varga 1, is x squared because of the varga with 1 as a coefficient x squared. Yavat 0, that's x multiplied by 0, and rupa 1 plus 1. So this is actually an equation where, rather than we do today where you put one side equal to something else, here you had them one below the other. The convention was to put it one below the other rather than either side of the equal to sign because it made it easier to subtract or cancel like terms. It was much simpler. And the other thing that you notice is that even if a particular power of the variable didn't exist, it was still represented there with a 0 coefficient. In modern convention, we would do this and completely omit this x squared, but they didn't do that. And here's another example. Both of these are from Prithudakaswamin. I'm going through this quickly. The first one is 197x, and now you'll notice they use a different coefficient. They use kalaka, so that is a different, a different variable. So kalaka is a different, that refers to a different unknown y, and since there's a dot above the 1644, it's minus 1644y, and then minus z, because now they use a different variable word again, nilaka, with a coefficient of 1, plus a rupa coefficient of 0. And all of this equals, it just equals a constant, but still all the different powers are represented. You have ya 0, ka 0, ni 0, and all of that finally equaling a constant of 6,302. Okay, or in our familiar way of doing it, where we don't put the 0 terms, that's what it looks like. So this is just to give you a sense of what equations look like as written by ancient mathematicians. Now looking at the verse by Sridhara, which actually tells you how to derive the quadratic solution, this is what it says. Chaturahata varga samai rupaihi pakshadvayam gunayet avyakta varga rupair yuktau pakshau tato moolam. And what does this mean? Pakshadvayam gunayet. Multiply both sides. Chaturahata varga samai rupaihi. So here again the varga refers to the coefficient of that varga. And so multiply it by 4 times the coefficient of the square of the unknown. So you're multiplying both sides by 4a, starting of course with this equation, ax squared plus bx plus c, and this is what you get. Then yuktau pakshau, to both sides you add avyakta varga rupaihi. You add the square, the varga of the coefficient of the unknown. So you're adding b squared, and this is what you get. So here the left-hand side is a perfect square, that's what it works out to. And then the next step is tato moolam. Take the square root of that. And so you get this, from where you can do some simple manipulation and get the familiar form of the solution to the quadratic equation. Sridhara uses this in his Trishatika to find the number of terms in an arithmetic sequence, starting with this well-known formula for the sum of n terms, which is a quadratic equation. We apply that earlier result, and this is what he comes up with to find out the number of terms in the sequence. Just as a contrast, I also have included Brahmagupta's solution. This is earlier to Sridhara. And here you can see that Brahmagupta only states what the formula is. He doesn't actually tell you how to derive it. He just tells you this is what you do if you want to find the solution. And it's varga chaturgunitanam rupanam madhya varga sahitanam moolam madhyenonam vargam dvigunodhritam madhyaha. So take the varga chaturgunitanam rupanam. So take the 4 times the coefficient of the varga, which is a, and multiply it with the rupa, c. You get 4ac. And then madhya varga sahitanam. To that you add the varga of the madhya, which is b. So you add b square. Moolam. Take the square root of that. Madhyena onam. Madhyena unam. Unam is reduced by the madhya. That's your minus b. And then divided by vargasya dviguna. So that is 2 times the coefficient of the varga. So this is basically just a statement of the result, of how you, of what the equation is, but not quite a derivation of this. And that's something that Sridhara explicates. Here's an example of the kind of problems that you see regarding quadratic equations. There are a lot of beautiful examples which include a lot of poetic imagery, and it makes it a lot of fun for students to work these out because they're full of very nice and vivid detail. This one here says, Partha Karnavadaya Marganaganam Krudhorane Sandade. Arjuna, getting enraged in battle, picked up a bunch of arrows in order to kill Karna. Tasya ardhena nivarya tacharaganam mulais chaturbhir hayan. So of the bunch that he grabbed, he discharged half those arrows and destroyed Karna's arrows. And then he took 4 times the square root of what he picked up, and with that he destroyed Karna's horses. Shalyam Shadbihi destroyed his spear with 6 arrows. And then Ishubis Tribhirapi Chatram Dhvajam Karmukam. So with 1 each, he destroyed his flag, his the canopy above his chariot, and his bow. Chicheda Asya Shirash Sharena. And then he cut off his head with one arrow. Katite yan Arjuna sandadhe. Tell me, how many arrows did Arjuna pick up? So the solution to this turns out to be a quadratic equation, making sure that you first assume that the number of arrows that Arjuna picked up is not x, but x squared. And once you set it up, you can apply your quadratic equation, which gives you an answer of 10. And remembering that we have to square that, we see that Arjuna, being the perfect warrior, even in his rage, picked up a random number of arrows, which turned out to be a perfect square. Moving on quickly to combinations. This is something that has been dealt with extensively by Jaina mathematicians, and I think I'm running short on time. So I'm just going to quickly state this very common result that we have all learned in school: NCR equals n factorial over n minus r factorial times r factorial has been pretty much stated in that form by Mahavira in his Ganita Sara Sangraha of the 9th century. Although it was known much earlier as well, but he's the first one to state it clearly that way. So I'm just going to go straight to the explanation of that. So it says ekadi ekottara padam, which means start with eka adi, and then go eka uttara, go one more and create a sequence like that. Urdhva ada stapya. Place that sequence in the numerator and in the denominator, krama utkramasha, in order and then in reverse order respectively. Pratilomagnam pratilomagnena bhajitam. Take the reverse product of the n minus r factors from the right, which leads in the numerator to r plus 1 times r plus 2, etc. to n. And in the denominator, if you take the last n minus r, it goes from n minus r minus 1, and so on, multiplied up to 1. And this, you can see the numerator here is basically n factorial over r factorial, and the denominator is n minus r factorial, which is your well-known formula. And that is the Sara. There's an example that he follows his formula by, saying, that was the other shloka that I skipped for lack of time, but this is what it says. Ganaka kathaya adhuna, tell me, O mathematician, yutanam rasanam varnan chapi bhedan. Tell me the different number of combinations as well as the composition of those combinations that you can make out of the 6 tastes: kashaya, tikta, amla, katuka, lavana, and madhura. Okay, so this is, usually when I give this talk to students, this is the audience participation component of my talk, because kids have just learned about combinations, or they don't know yet about it and they have to figure it out. It takes them a little bit of time, but they eventually do get to the answer, which is 61 plus 62 and so on up to 66, and that's the answer. So when they do arrive at the answer, I like to give them a little pat on the back by quoting this verse from Bhaskara's Lilavati, which comes after he introduces combinations. And it says, na guno na haro na kritir na ghanaha prishtas tathapi dushtanam garvita ganaka vatunam syat pato avashyam ankapashesman. Which says, in this ankapasha, this snare of numbers, which is what he's referring to when he's talking about combination problems, there is no heavy-duty multiplication or division, no squaring or cubing. But still, if you put this question to an arrogant but unskilled mathematician, it's sure to cause his downfall. So it makes the kids feel pretty good, and I tell them take that as a pat on the back from a mathematical genius of 800 years ago. I think I will skip this. Fibonacci numbers, you all know the way it's generated, the sum of 2 numbers adding up, making the next one. The golden mean is related to this sequence, which is commonly used in architecture, painting, etc. That's an example where you see it. And this was named after an Italian Fibonacci who traveled widely throughout Africa and the Mediterranean, is credited with popularizing the Hindu numeral system in Europe. But you do see an awareness of Fibonacci numbers in Pingala's Chanda Shastra of the 200 BCE, and in the works of later prosodists, Virahanka, Gopala, and Hemachandra. They were dealing more with problems of poetry. Hemachandra's problem was how can you take a line of n beats, and how many ways can you fill that up with different combinations of long and short syllables, and he hit upon the insight that that is actually the sum of two terms, the number of ways in which you can fill up a line of n minus 1 beats, and add the number of ways you can fill up a line of n minus 2 beats, which basically mirrors the Fibonacci sequence, and this is his sutra, Ankantya Upantya Yoga Pare Pare Matranam. So in a sequence, the next number is formed by the yoga, the addition of Antya and Upantya, the last and the next to last. It's very succinctly stated. And this is an instance which I won't really go through now, but since I do give this talk to students of Sanskrit also, I give this to them to encourage them to read through this material, because this is actually a section of Hemachandra's commentary on his own sutra that I just quoted, and it's very simple to understand by even an elementary student of Sanskrit, because he's basically just talking about how you generate the Fibonacci sequence. Take 2 and 3, add it, you get 5. Take 3 and 5, you add it, you get 8, and so on. It's very accessible. So I want to take a couple of minutes just to talk about what we are doing at the temple to popularize Indian mathematics among students. And this is an instance I mentioned to you that we create these little modules on Indian mathematics to share with students whenever we can. These are a few sample pages from a workbook. The one on the bottom left actually is the problem that I just told you about, the one relating to Arjuna and his arrows. The one up here is a combinations problem, which talks about Shiva having 10 arms, a different weapon in each arm. How many different ways can you create statues with all the different combinations? The one next to that is a Pythagorean Theorem problem, 2 monkeys on a tree with a well on the side. One monkey down the tree and goes straight up to the well. The other one climbs up and takes a flying leap along the hypotenuse into the well. How much further did he climb up the tree? The last one is about a miser giving alms to a beggar. They all have nice, interesting situations which get the kids involved and give them a sense of, the mathematics. It informs them that the mathematics that they do now and they think of as modern mathematics is something that students of mathematics worked on so many hundreds of years ago in India as well. And this is something that I just included to give you a sense of how I've seen math textbooks. These are typical math textbooks in the United States that school children use, and they seem to do a really nice job of incorporating mathematical history. These 2 somewhat brownish pages are from a calculus textbook, where there's a reference to Ramanujan's series of pi, and it's accompanied by a small sidebar with some information on his life and work and so on. There's another one here about the invention of calculus in 17th century Japan. A couple of snippets of information on the big fight between Newton and Leibniz over who actually discovered calculus. And even some bizarre and obscure information like this one here, which talks about a pauper, a poor guy in 15th century Italy, called Tartaglio, I think, who somehow mysteriously came upon a formula for solving third-degree polynomial equations, and that came to the attention of a very celebrated mathematician of that time, who approached Tartaglia and somehow convinced him to part with his secret, promising him money and fame and so on. So he gave it to him, which he then proceeded to publish as his own result, and in addition got a student of his to accuse the other poor guy of plagiarizing his work, with the result that there was so much of an academic outrage that he had to run away from that town to save his life. So these are just instances of inclusion of different bits of mathematical history to give students a sense of the people, the personalities, the issues at stake, and so on around mathematics, and make it more interesting to students. And I think this is something that we could probably think of incorporating into our own textbooks here as well. Looking ahead, when I was a student, a college student, my knowledge of Indian mathematics was basically that. India had sent up its first satellite some years back called Aryabhata, and I knew that the satellite was named after an Indian mathematician and astronomer. That was it. And it wasn't really, what I knew was not thanks to the Indian educational system, but the Indian Postal Service. Not that the Indian Postal Service was unique in that regard. There were other countries, large and small, that also issued commemorative stamps in honor of Aryabhata, the satellite. Poor Bhaskara never got that honor, neither for himself nor for the satellite named after him, although the Russian government, the then Soviet Union, did issue postal envelopes in honor of Bhaskara and Aryabhatta, both the satellites, not the mathematicians. That was the state many years ago, many decades ago. I think the situation today is very, very different with the holding of conferences like this, a lot of publishing of popular material, technical material, a surge of interest in the subject. So it's my hope that in the years to come, we will see that the typical well-educated student of India has a pretty good sense of his or her intellectual history, certainly more than can fit onto a postage stamp or even the front of a postal envelope. Thank you very much.